Oh, okay. Good. Perfect. So, so far we have been working on a single point calculation rate, but we are not limited, or the software doesn't limit you to only do one calculation at a time. The software has the option to do what we call, or what I call internally at OLI, single surveys, dual surveys, and even if we don't have a specific type of calculation that you want to do, you can create a survey by changing the single point calculation type that you want to do. So again, you can do surveys by temperature, pressure, composition, anything that you want to understand, and the variable that you want to understand. Usually it's temperature and pressure. The other one is the composition of a specific chemical or component that you have in your water, or gas or oxygen or things like that. In other cases is more like pH, or what happens if I don't know, change ionic strength, things like that, you know? So I just want to show you at least one example of how to set up these survey calculations, because they are more, in some cases, they are more, they give more information of what you are trying to do, especially if you are designing an experiment. So what I want to do now is just to do a simple temperature single survey. That's how I call it. And then we will switch to the dual surveys and learn how to calculate these heat maps for corrosion rates, to see what happens with corrosion rates when you change two variables at the same time. Okay, so let's go back to the software. And what we are going to do first is, as usual, add a new stream. Okay. Again, what I want to do with this calculation, with this stream, is I want to calculate the corrosion rate of a stainless steel 304 as a function of temperature. And the chemistry that we will have, it will be mostly water, CO2, and sodium chloride. So let's change the name of this stream. Let's change it to corrosion rates surveys. Okay. We're going to do the AQ framework. Is the next thing that we need to do. And the second thing I want to do is to make sure if I'm happy with my units. Do I want to work in moles? Do I want to change? It's okay. So maybe you want to change some units. Metric batch moles is the units. If you want to customize them, you'll see that all your inputs are in moles and all your outputs are in moles. And I think it's okay. We can work with mole units at the moment. So let's not make any changes. But remember that that's one important step. Always make sure that you're changing the units before doing any simulation, so that you reduces frustration time later on when you're analyzing the results. So for the inflows is my chemistry. So water will be the default. Of course, I need some water. I have some CO2 dissolved in this water, or not dissolved, but I have some CO2, and that is 1 mole. We will need to figure out if it dissolves completely or how much of it dissolves, etc. We also have some, how do you call this? Buffer, which is the sodium bicarbonate, and I entered wrong, so it's NaHCO3. This is the sodium bicarbonate. So it's a buffer, help us keep the pH more or less in the value that we want. This is usually used in autoclave charging. And then we have sodium chloride, 1 molar. So we have a 1 molar solution of sodium chloride with sodium bicarbonate and CO2. And you can always, just because I'm always curious, you can always add a single point and calculate what are the properties of this solution, right? Just to get an idea of what you have as a starting point when you're doing a calculation rate. So again, I ran this isothermal single calculation point, and I'm seeing here that this system is mostly aqueous. And I do have a small amount of vapor. So again, my curiosity takes me to the report, and I start checking what is my vapor, why am I having a vapor? And you'll see, sure enough, you added 1 mole of CO2, but it doesn't mean that all of it dissolves in water. Just a portion of it, and the rest of it also goes, well, it goes in the vapor phase. And because you were adding CO2, maybe it was too much, it evaporated a little bit of water as well. Okay, so maybe imagine an experiment where you are just bubbling CO2, and it was just too much that most of it went out, and it just also got some vapor out of the system. So that's what it means, or that's how I interpret it. Maybe you have a different interpretation, but that's how I see it. You'll see that there is a change in the pH. It's not 7, it's 6.30, it's 6.4. It went low again, maybe because I was adding my CO2. I am dissociating that CO2 in water, and that's producing bicarbonate ions, and it's increasing probably my composition of hydrogen plus ions. Okay, so that's my little understanding of what's happening in the bulk solution. But you want to understand now what happens if you start changing temperature of this chemistry, the temperature of this chemistry, and how it affects the corrosion rate. So this should be very simple by now. The second step, or the next step that you do, is simply go add corrosion rates, right? So just click on the corrosion rates. This will bring this screen here. You are already familiar with the screen. But what we are going to do differently is that we are going to select the temperature, the survey as a temperature survey. So here to the right, we have always selected a single point rate, but today we said no, we want to change the temperature of these calculations. And notice that the software by default selects a range going from 25 degrees C to 100 degrees C. A total of number of steps of 15, and the step size 5 degrees C. This is the default, but you don't want to go by the default. You want to change the default. So you go to specs, which is right in front of temperature. And in here, this new window appears, and you can change your defaults. So maybe we want to study this going from 0 degrees C and 60 degrees C. Okay. Now, one important thing to highlight here is we cannot go higher than 100 degrees C here. Why? Because we are operating at 1 atmosphere. We will be boiling off this solution, and at some point, everything will go to the vapor phase. There will now be an aqueous phase, and then there will not be a corrosion rate. Something to keep in mind. 65, sorry, let's do 65. And then the increment is going to be, you know what, you say, no, I don't want to set it up by increments. I want to set it up by number of steps. So you click on the button here, and change from 13 to 20, and I want 20 different steps. And that will be every 3.25 degrees. Of course, you can do it differently. Maybe you say, that's weird. Maybe I have to do it at 2 I want to do it every 2 degrees C, etc. But the thing is that as you add more points, the calculation time is going to take longer, right? So your calculation speed is going to be decreased. But if you want more refined data, you can always add here 100 steps, 200 steps, etc. Okay, that is how we set up here the survey temperature. Another thing I want to highlight here is you'll see in the category section, you can also change from which potential to which potential you want to do the sweep for the potential in a polarization curve. You can also set the increment, play with that, how you want to visualize that polarization curve. I have never, ever in my life moved this. I haven't had, I haven't had the need to do that, but the option is there. Calculation type, same idea. So a survey, this survey will be done isothermally, right? Because I'm changing I'm going to keep the pressure constant, but I'm going to change temperature. And I'm going to define the temperature, the 20 different temperatures. But again, one more time, you can always do any other type of survey calculation that you want to do. Maybe you want to calculate the dew point, the set pH, etc. The option is there for doing those type of surveys. And these calculation options here, I haven't talked about this, but basically these are the properties that we turn on by default, which the ones are checked. In some cases, you want to do or see prescaling tendencies, total dissolved solids, etc., heat capacities. And we don't turn them on by default. We leave them off, again, because it will increase this calculation speed. And we want to be as fast as possible. So if you want those properties, you can always come here and turn them on. But at the moment, they are turned off. Okay, click OK. And that will change my temperature survey range here from 0 to 65. That's how I want it. And another important step is to change the contact surface. We said that we want to study this for carbon steel, for stainless steel 304, because we have done too many examples with carbon steel. And we scroll down, look for stainless steel, pick it. Software likes to show what compositions you have for the different allowing elements in your contact surface. If you want to double check you selected the right alloy, just hover over the contact surface and you can see it says stainless steel 304. Okay. Let's change the name of these rates. Rather than call it rates, let's call it corrosion rate versus temperature for stainless steel 304. Let's try to be specific so that we don't forget what we are doing. And nothing is wrong. Everything seems okay. The calculate button is green. We can go ahead and calculate. Now, this general corrosion rate tab makes sense that is actually in a plot, right? In a plot view, because now the software is going to plot by default the corrosion rate as a function of temperature. Okay, so in here you see that the software is plotting your corrosion rate values and it's showing a trend. It's saying as you increase temperature, you have an increase in the corrosion rate. That's usually what we see, what happens in real life, in experiments. As you increase temperature, you see an increase in the corrosion rate. And of course, the software always likes to plot this pH, but maybe you don't care about the pH. is not going to give you any a lot of information, and you'll see that the pH really doesn't change like by 1 unit, but maybe there are other variables that you want to also plot and see why you're having the corrosion rate that you're having. So you could say, well, this could be CO2 corrosion because we are using a sample that has CO2 dissolved in it. And we want to see how much CO2 is dissolved and how much it leaves the solution as I increase the temperature. So you go to variables and you can start adding any of these possible properties or results that you want to see as a function of temperature. There are many categories. And this is basically the summary of everything that we had in that report table, but just put here in a list. So you have stream parameters, the calculation results, the corrosion values. You see that the corrosion rate is there. The pH is there here. That's part of the additional stream parameters, but maybe you don't want the pH. I'm interested to see what is the composition of CO2, or what is the concentration of CO2 in the aqueous phase. So I go to the aqueous category and expand it and see and double click this value or select it, and I'm going to put it in the Y2 axis. So I select it and I use the arrow to go to the Y2 axis and then click apply. And then you'll see now changes here. The pH is no longer there. I'm adding the CO2 aqueous composition. And you'll see now as the temperature increases, sure enough, you see a decrease of CO2 in solution because you are just basically making the CO2 go or bubble out of the solution. So that's what's happening. So if I have less CO2, why am I having more corrosion rate, right? So that's another way. That's another question that you say, okay, why if I am decreasing my CO2, why am I having a higher corrosion rate? So the next step is, okay, let's analyze if we have localized corrosion. We don't have the passivation, in this case, is saying that we don't have any localized corrosion. The repassivation potential is always above, at all temperatures, above the corrosion potential. No tendency to pit. It will only corrode, and it will corrode at this rate, 0.0018 millimeters per year, or in this range will be the corrosion. Polarization curve. So in here is where you can start seeing the effects of temperatures and temperatures in this case. So if you go to variables, and I'm going to clear all of these reactions, and maybe what I want to see is the net current density for now. That is at 0 degrees C. But I increase the temperature to 26. Click apply. You start seeing an increase in that anodic response. Okay, 52. An increase in the anodic response. And so on and so on. So basically, the temperature is having an impact here in this case on the anodic response of these stainless steel 304, right? So you start seeing that as you increase temperature, the anodic current density, or this passive current density, also increases as a function of temperature, and that's what's one of the reasons why you start seeing an increase in the corrosion rate. Okay, and you can also see the effect probably on, since this is CO2, you say, okay, what about my bicarbonate reduction reactions? Oh, I don't see any. That's weird. Let me see this one. bicarb, that was hydrogen, and you start analyzing what happens to the other reactions, right? For some reason, bicarb doesn't even seem to have an effect at all here on the driving the corrosion rate. So it seems it's purely due to temperature here. This is weird. I don't understand. 1 second, please. Oh, maybe it's the proton. Yeah, it's the hydrogen. Okay, so yes, we are adding CO2. That CO2 is decreasing the pH of the solution, and the main reaction that is driving corrosion is that hydrogen reduction reaction that is happening on the surface for this stainless steel specifically. Okay. Any questions about these surveys and how you can just now visualize the results as a function of a variable, single variable? Let me see one more thing here. Okay, so that's how you set up that temperature survey. The next example I have is, okay, what if now, rather than just changing temperature and pressure, I also want to change pressure, or I also want to change the concentration of sodium chloride. In this case, it's actually the concentration of sodium chloride. What happens to the corrosion rate if I start increasing the salinity of my solution? And also, while at the same time, I increase the temperature. So that's what I called a dual survey. And that's what we're going to learn how to set up in here. Okay, so we have our single point, our single survey. The next step is, okay, I want to add an extra variable to this study. So I'm going to use or reuse the same corrosion rate survey that I did before. So I'm going to right click on it and copy. And then right click on corrosion rate surveys and paste. Okay. So for this corrosion rate, let's change the name. I'm going to simply make a change here. Corrosion rate versus temperature and NaCl, or salinity, or chlorides, or however you like to see it. We want to see how these two variables change the corrosion rate. So everything remains the same. Everything, we brought the same idea, the same calculation that we did before. Isothermal, static, we have the inflows, and we have our stainless steel 304 contact surface. Okay. To the right, we have defined the temperature survey. And we said that goes from 0 to 65 degrees C, and with a number of steps of 20. Okay. But now we also want to add a second survey, a second variable. And that would be done here in the next drop-down bar that you see here in this button. So it says survey by temperature, then by. So when we don't select anything, it's just a single. But we want to select here composition. And you'll see that we have less options here. We have temperature, but because we selected temperature, is grayed out. Then we have pressure, composition, and pH. So we are kind of limited with the amount of the second variable that we can select here. But I want composition, so I'm going to select composition. You see that this button here is red. It's saying, okay, which composition of which species. Is basically saying that down here. Component not selected for composition survey. We need to make sure that we are that we instruct the software which component we are going to vary. Another thing is important to point out here is that you can vary these two different variables either independently or together. Independently means the temperature is swept from 0 to 65 at the first composition, and then it goes to the second composition from 0 to 65, and then the third composition from 0 to 65, and so on and so on. Together means the first composition with the first temperature is one set and is run. The second composition with the second temperature is run. The third composition and the third temperature is run, and they are always going to be coupled, right? So it's going to require less calculation time, actually. It's not going to require as many data points. So we are going to use this, I want to run this dual survey as an independent, because I want to see at one composition what is the effect of temperature, and so on and so on. So we are going to leave it independently. What we do need to specify is the composition, the component. So let's click on the specs. And anytime that you see a red button here, usually you need to click on the specs button to specify the variable, or specify a target or something like that. So in this case, the component I want to vary is the sodium chloride, the salinity. So I select the sodium chloride. But I also have to specify in the survey range the composition. It's in moles. The unit will be here. And I want to go from no salinity at all, so no sodium chloride at all present in my water, to saturation. So the saturation of sodium chloride is around 5.5 moles of sodium chloride in water. And that's the amount that I want to, that's the limit I want to reach, the saturation limit of sodium chloride in water. I also want to calculate 20 points. So that will give me a matrix of 21 by 21, because we also have the first step. So that will be 121 points, right? Now I don't know, yeah. And this will be how we set up the composition survey for my second variable. So after this, you can either apply or OK. They both do the same. The OK button, however, closes the window. So you double check here, and you'll see the temperature survey here is 20, is going to be number of steps 20, plus the first calculation is going to be 21. Composition survey, number of steps is 20. And I was wrong, totally wrong. It's number of the total amount of points that are going to be calculated are 441 points. So it's going to be a very well refined plot that you will have. Okay, let's save, because you never know. And once you have a specified temperature and composition, then you can go ahead and calculate. Now, this is going to take a little while. I don't know, maybe 2 minutes, depending upon how fast the machine is. We can go to the general corrosion rate, and you will see that by default, the plot here is, again, the corrosion rate as a function of temperature, and of course, the pH to the right. Okay, well, it wasn't that bad. It just finished the calculation. Save. But sometimes this view is not, it's not as easy to understand what's going on, right? Maybe if you would remove the pH, it will be more understandable. You can see better. but your legend is really big, etc. So you can see here, you're seeing that as the temperature increases, overall the corrosion rate increases for this carbon steel. This is not news to us. But you can also see that different data points here mean different salinities, right? So goes from low to high. Seems that the one here at the top is the low salinity, 0 moles, and as you increase the moles, the corrosion rate goes a little lower here. Okay, what about the localized corrosion? So I increase salinity, and I don't see that I'm having any localized corrosion at all. The corrosion potential remain more or less the same. The chlorides seem to have moved a little bit the repassivation potentials, but they never touch. They are far away. They are far away from each other. The repassivation potential driving force is higher than the corrosion potential, so no localized corrosion damage. So if I go back to the general corrosion rate, and I want to really see this more like a matrix, you will see that to the right, here where it says options, variables, view data, you also have these icons. And there is a contour plot type of icon. So if you click on it, it will give me a plot here where it's telling me the x-axis is the temperature and the y-axis is the sodium chloride concentration. Okay, and it's saying the lowest corrosion rate that you can see is 7.92, 10 to the minus 5 millimeters per year. And the highest is here at the highest temperatures, and is 1.99, 10 to the minus 3 millimeters per year. Now you'll see that this is more visual, right? You can see that the results are like much easier to interpret if you see it by colors and see what's happening. And you can see that the sodium chloride concentration for this specific alloy at these temperatures is now having a huge, like it's almost independent. Like if you were at low temperatures, it's almost independent on the sodium chloride concentration. So that sodium chloride concentration is really not impacting the corrosion rates very much. Okay, you can also see other variables. What happens to the solubility of CO2 as you increase temperature and also as you increase the salinity. So you can always go to variables, and that will open a new window. You go to the aqueous phase and then look for the solubility of CO2 rather than the corrosion rate. You want to see what happens to that solubility. And then in here you will see the impact of the salinity in this case now, and temperature and the solubility of CO2. The lowest solubility happens at higher temperatures and higher salt concentrations, and that makes sense. There is, as you increase the temperature, you're removing the CO2 from the liquid phase, and also you have the salting out effect, where when you increase the concentration of a salt, the solubility of gases like such CO2 also decreases. And only when you have low temperatures and low concentrations of sodium chloride is where you have higher concentration of CO2 dissolved in solution. So all of these insights you can get and understand what could be happening or causing happening in the bulk chemistry that can cause an impact on the corrosion rates of the system. of the alloy. Any questions about this? Easy, right? Easy peasy. Okay. So that is the dual surveys. I'm not going to spend more time on it. I want to move to the next and last topic, which is entering water analysis using the software. And this one is important because I will be talking about what Mariana wanted to talk last time about the oxygen concentration. We will be doing also a survey using this produced water chemistry. So it's relevant. Let me see. So yeah, this is what we're going to do. So if there are no more questions, I'm going to jump to this next topic. Maybe I can just give an introduction and then we can go for a break. And then we can start working in the examples, with the examples. So far, using the software, right? We have been entering data as a molecule, right? Like all the chemistry is a molecule. So we say CO2, in this case, sodium bicarbonate, sodium chloride. We never enter any type of ion. So if you are given a produced water analysis or a geothermal water analysis, they usually come in what we call an ionic input. Okay, so the software fortunately has the option to enter this type of water analysis, and you are not limited in some cases. With some other simulation softwares, you have to do conversions and figure out what molecule you can use to reproduce that water analysis. So fortunately, in the software, we have that option. And today, one of the examples I want to do is for that usually when you're doing corrosion analysis, like I said, you do produced waters, geothermal waters, or also seawater. Seawater has a lot of ions and a lot of ions and a lot of neutrals dissolved in this water. So they have oxygen. They also have, we know that it has a lot of chlorides, magnesium, calcium, and all of this. We also know that seawater is very corrosive, okay? Because it has the chlorides, the oxygen, it attacks the passive film of steels, and you see that both there, it has suffered severe corrosion damage. And also, this type of waters they cause a lot of localized corrosion damage, right? So pitting would be one type of localized corrosion that happens a lot and is seen in materials that are susceptible to this damage. This water usually induce this type of localized corrosion damage. So what we are going to study here in the next example is we are going to learn how to enter this water analysis. And then I'm going to show how to then do surveys. Let's say if you have oxygen, if you have chlorine, if you have some other components, how to study the effect of these different components in the water, in the seawater. And hopefully this will give you an idea of how to enter any other water analysis that you may have that come to you from a different lab, from a different company, and then you enter it in the software and learn how to do it. Okay, so with that being said, let's start. What should we do? Should we go for a break first and then work, or should we work for a little and then go for a break? What should we do? It's almost the top of the hour. Who has a say?
A break from my side, please.
Okay. So let's come back. 11:04, my 11:04, 4 minutes past the hour. And then we can start with the next example. Okay?
I'm back.
We are back. We are back.
Back. Yeah, Irfan's back.
Perfect. Everyone is back. Okay. This is the last hour. We are almost there. We made it. Almost made it. Okay, so I was talking about water analysis and how we are going to learn how to enter them in the software. And to be honest, that's really, 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 really simple. You will see. You will see that. The first thing that I'm going to do is save, just in case I haven't. The second step is, like I was mentioning before, we have entered only streams. Stream. But we also have another option in the software. And we need to click on this global stream. When you don't see the icons that you want to see here, you click on the stream, on the global stream icon, and then that will bring all your objects. Now, here, when you have access to the stream analyzer, you have access to these 3 different icons here. One of them being the water analysis. When you have access to the ScaleChem software, you will also see something that is called a brine analysis. And they're basically the same tool, the same thing. But for the ones that don't have a ScaleChem, you will see the add water analysis. And that's the one that we're going to use, okay? So let's double click on the add water analysis. And you'll see that the icon is slightly different. It's actually different. It's a bigger compared to a little water drop. So this water analysis, we're going to rename it. We know that it's a seawater analysis. So let's just name it seawater analysis. And the next step is, since we are going to use this water analysis for a corrosion rate calculation, what do? We change it to the AQ framework. That's the first thing we do. Okay. Now, the water analysis that was provided to me, usually, well, it's obviously comes in probably in a Excel spreadsheet or in a PDF, but this is the water analysis that was given to me. So I have some cations and some anions, and notice that it doesn't have any molecules or dissolved oxygen or CO2 or H2S. In some cases, you will see a third section where it will specify that you have some dissolved gas in that solution. So this is what we're going to enter. So we'll go back. And in this water analysis, so these analysis parameters, you'll see it's different. It's slightly different than what we are used to when entering the data. The stream amount, temperature, and pressure is the same. But what this means is these are the temperature and pressures. Temperature and pressure that the water analysis was performed in the lab. So usually I assume 25 degrees C and 1 atmosphere. That would be the temperature of the lab. In some reports, I have noticed that they put the actual temperature and pressure that they use in the lab to do the measurements. So if it were 22 degrees C, you can change it here, right? But overall, we will assume 25 degrees C and 1 atmosphere. Additionally, in those water analyses, in some cases, they report properties like pH, like TDS, total dissolved solids, densities, electrical conductivities. And usually the value that they report is pH, and in this case is 7.6. And and also the alkalinity. The alkalinity is another value that is measured. In this case, it wasn't given to us, but it was given to us. What it was given to us was the density value. So the density value is down here, and that value was 1.023. Now, why do we enter these recorded properties? The software can calculate these properties, but why do we need to enter them? And the reason why we need to enter them, we don't have to, but we should enter them, is so that you can see how far away or how close the software is to these measured properties. And I will be showing you what I mean by that in a moment. But ideally, the software would be able to predict that the pH is 7.6 and that the density of the solution is 0.23 because it was measured in the lab. So we should match those values. And if we don't, well, then we need to ask ourselves why we are seeing those differences. And then something that is called the reconciliation step is where we have to start playing or using it to make sure why we are not matching those measured values. Okay, so there are more sections here. This is what I was saying. Neutrals. Neutrals means molecules, like we have been doing so far. But in some cases, it's reported that in produced water you have CO2 dissolved, H2S dissolved, silica, boric acid, oxygen, etc. We don't have any of those. It wasn't reported, so we don't enter any value. These total ions here, this total ion section, is actually a newish, not that new, but it was added very recently. This section is because in your water analysis, you will see that they will put values as P, as I, or B. They will report the ions as P, Si, and B. The P, or Si, or B, phosphorus, silicon, and boron, they don't exist in real life. They don't exist like that, like they don't exist as P or Sie or B. They exist as an anion, for example, the P could be as a phosphate, right? Or if you measure Sie, that means that you find it as silicon oxide. And if you measure boron, that means that is boric acid. So the software, when you see those numbers, you simply enter the P, S, I, E, and B values here, and the software will make those changes for you. It will convert the P into a phosphate, etc. I haven't seen the very much use of this because I've seen people that immediately converted and entered it directly here as SiO2 or boric acid or some other component. But it's good to mention why it's there and what it means. Cations. This is easy. Cations is everything that has a positive charge. So in here we will enter that this water analysis has 10,500 milligrams per liter of this ion. For potassium is 380. For calcium is 400. For magnesium is 1,270. For strontium, 13. Barium, 0.1. And also some iron was measured in this water. You can always change the units. Some cases it's no milligrams per liter is another unit. You can change those units here. Okay, in concentration. Sometimes it's in ppm, etc. So you can always make those changes directly clicking on the hyperlink. For chlorides, 19,000. Sulfates, 2,650. Oh, I put it wrong. 2,650. Bicarbonate, 144 bromides. No, this is not bromide. So the next component is the bromide. That's what I have in this PowerPoint here. So we have interchlorides, sulfates, bicarb, and we have the borates, and we have also the bromide. But I don't have them here, so how do I enter them, right? So I'm going to delete this bisulfide, and I'm going to delete this acetate ion. Just with the delete button in my keyboard, okay? And what I'm going to do next is, when I am entering an ion specifically, if it's the bromide, so I enter the element Br, and then I have to define the negative, right? Because it's an anion, oxidation state. So we know that the bromide, I think it only has one oxidation state, so we will put -1. If you have doubts, if you don't know how to enter this specific anion, you can always click on the drop-down arrow here, and the software will help you. So you will see here, the software says bromium. You could have entered it as Br1-, but it's the same ion, bromide ion. This is the OLI name. You could have entered it as Br-, but it's the same ion. Or you could have entered it just like we did, Br-1. So you select one of the options, and the software you can select that, and the software puts it in there for you. The bromide ion is 65 milligrams per liter, and I also have the borate ion. So the borate ion is a little bit more tricky. But maybe, let me see, borate. If I put borate ion, no, it will not help me with the borate like that. But I know that it's boron, so let's see, boron. And I know that it's the borate, so it's BOH. You start seeing here that the software starts helping you a little bit, right? And all of them are the same, borate. So we select this one, or we can just simply type it, right? Oh, this is the boron tetrahydroxide ion. That's how the software calls it, boron tetrahydroxide ion. And that's the ion that we're going to enter. Maybe I should just, in the next example, remove this because it's a little confusing. But the point with this ion here is that we can enter complex, different complex ions that we see in those water analysis. Okay, so that's how we enter the data. Any questions about how to enter, what the things mean here, etc.? Okay. So once we have entered that water analysis, the next thing we need to do is calculate the properties. So just like when we do a single point calculation, and we want to understand what is the pH, what is the speciation, what is all of that. Like, we need that report. That's what we will need to do next. So you will see here it's slightly different. To the right, you will see a button that is called Add Reconciliation. Think of this as add calculation. Like if it were the exact same option as add a calculation, but here is add a reconciliation. Just click on it. And that will create a reconcile or a sub-calculation under the water analysis. The reconcile option here to the right, well, you have 4 options. You have an option to, I don't like this name, it says not reconcile, but what it means is that you're using the concentrations of these anions and cations to calculate the properties of the solution. You are not going to use the pH, you're not going to use any other variable. Only the concentrations of cations and anions will be used to calculate the properties of the solution, and the software will calculate if there are missing anions and cations to keep this water electrically balanced, because you cannot have any positive or negative balance charge here. So this not reconcile, that's what it does. It's going to do a reconciliation and charge balance, basically. And then you have another option here, reconcile pH. So the reconcile pH means it uses the cations and anions concentrations and also the pH that was measured in the lab. So it will adjust the pH in such a way that you will match the 7.6 pH that was measured in the laboratory. And same with the pH alkalinity and also the pH alkalinity and total inorganic carbon. But I'm not going to go into details. In the manual, there is more details about this. I usually, as a best practice, go with the not reconcile option first, just to see what the software is calculating with the data that was given. And then compare how far away we are from the measured values. So click on the not reconcile option and then click on calculate. Okay, so the calculation was completed. To the right, again, you'll see the summary of what happened, what the software has done. It had to do a charge balance. It measures how many cations and equivalents per liters you have versus the anions, and you'll see that there is a negative imbalance, meaning that there are more anions in solution than cations. So the software has to add sodium plus to reach the electron neutrality. And I'll show you that in more detail in a moment. Then you have the phase amounts, says that you have an aqueous phase, and then you have a solid phase. And this is the pH of that water analysis. Then you go to the report. The report, again, is going to be slightly different because this is not a stream, this is an ionic stream. So this is what I was talking about, why we enter the values in this section here, right, in the recorded properties. These recorded property values will come here to the report, and you can now compare what was measured versus what was calculated in the software. So in here, you'll see that the pH calculated by the software is 7.53 compared to the measured 7.6. I call this actually a very good match. I don't think we need to do any type of reconciliation by pH or anything like that. The density value is also very close, so we shouldn't worry about that. So I would say measured values versus calculated values are good, or they match, they're similar. And then you can start seeing, scrolling down, this is what I was saying, the charge balance. It calculates the total cation and anion charge, the negative imbalance, and which ion it picked to make sure that this water was balanced. It added more sodium, so that means that it had to add almost 80 milligrams per liter. The difference is 0.76. That's also very small. And this is a very important piece here, this table. When people give you a produced water analysis or a geothermal water analysis, and you come here and you see that the software had to add maybe too much of a cation or too much of an anion to reach electron neutrality, maybe this value becomes 20, 30%, 40%. That means that that water analysis is wrong. and that you shouldn't be using it. Okay, always make sure that your difference here, this percentage difference, is less than 10%. If you have a huge number here, this will definitely not be representative of a good water analysis sample. Maybe either we enter the data wrong in some place, we mistyped something, or maybe then the laboratory did not measure an important cation or an important anion that was part of the water analysis. So this table is, I always recommend to come to this table and make sure that you don't have a huge difference here. It has to be less than 10%, or else your water analysis is not good. And of course, these are the properties. You're already familiar with these tables. These are the scaling tendencies. It tells you what you will be precipitating out as a scale of that water. And the speciation table. So how much of the chloride you actually have, potassium, etc. All of this speciation table. Okay, so that's the water analysis. And we analyzed that this probably is the one step that we spend a lot of time on, because we want to make sure that we have a good water analysis to then do all the corrosion rate calculations that we want to do. If we have it wrong, so we are starting from a bad reference. So that's why I spend so much time here on teaching you how to understand the water chemistry. Okay, so now we are happy with this water analysis. We're happy with the prediction, the pH, everything is matching. Now, what I want to do is start doing corrosion rate calculations. If you remember, no oxygen was reported. This is ocean water, and it is exposed to oxygen daily, right? So we should have oxygen dissolved in this solution. So we need to make sure that we are going to account for that oxygen concentration in this water analysis. So what I'm going to do next is, I'm happy with this reconcile option. So right click on it and add it as a stream. We're going to start using it for corrosion rate calculations. And that opens a new window. I have shown this window before. And what this window does is, anything that we enter as an anion and a cation and all of this is going to make it, it's going to convert it into a molecular stream. Why? Because the software likes to keep everything electroneutral, and if you keep anions and cations separate, it just complicates things. So let's just change the name to molecular seawater. And we are going to include all the phases, aqueous, everything. We are not going to complicate our lives here. So this is my water analysis that I'm going to use for any corrosion rate calculation that I want to do from now on. Notice that, as I said before, it's not going to bring any cation or anion at all. Everything is put into a molecular form. Okay, and these molecules, when you put them in water, when you dissociate them, they should give you the exact same composition as that water analysis that we entered. So that is the equivalent, molecular equivalent of that water analysis. So the next step is, notice that in here we don't have any oxygen, right? So we're going to, under the inflows, we're going to enter the oxygen oxygen molecule. And we don't know, in this case, how much oxygen we want to add to this water. What I want to do is, I want to find the critical concentration of oxygen in this seawater analysis that will lead or will start causing localized corrosion damage on my stainless steel 304 at 25 degrees C and 1 atmosphere. okay, at room temperature and pressure. So to do that, I'm going to add a survey, okay? So for that survey, what do? We go to, because it's going to be a corrosion rate. We are going to go here and we are going to add a corrosion rate calculation. Okay, that will be a corrosion rate calculation. Now it's showing survey by single point rate. So what I want to do now is, okay, I want to vary the concentration of oxygen from one value to another value that I don't know yet, and see what is the effect of that oxygen on my corrosion rate. So I will do a survey by composition, right? And I will do this on a carbon steel. So let's select here. Let's go. No, this is not carbon steel. Stainless steel 304. So click on stainless steel 304. This is the composition, chromium 19%. And I'm going to change the name of this corrosion rate study. I'm going to say oxygen effect on 304 stainless steel. Okay. Okay. So notice that my calculate button is saying it's red. Something is wrong. I scroll down and it tells me I haven't selected the component. Of course, I haven't selected the component. I need to go and select the component. The software doesn't know if it should pick the boron trioxide, iron chloride, doesn't know. So we need to go to the specs button that is next to the composition button, and we are going to select look for oxygen. We had entered oxygen here, so it recognizes it as one inflow. And then we go to the survey range. For the survey range, we are going to say that we're going to maybe, we don't know, this composition, these concentrations are going to be from very small to very high concentrations. So maybe it's a good idea to work in the logarithmic scale. So let's select the logarithmic scale. Because it's a logarithmic scale, the software will not let us put a 0 there in here for the first point. So we have to select a very small value. And I think 1 parts per trillion is good. This is in milligrams per liter, but I guess we can do 1 10 to the minus 5 milligrams per liter. And then we can go up to 10 ppm. I think the oxygen value when you dissolve it in water is like 8 ppm, but we can just go a little higher and say this is 10 milligrams per liter. Okay, number of steps 10. We can put 10 here, or you can put your well, in this case it only allows you to put the number of steps. Okay, we have defined the concentration range from a very small value to a very high value of oxygen, basically above saturation. And we are going to see what is the impact, right, on the corrosion rate. So click OK. My button here, the calculate button, is green, and it should have changed for you as well. And make sure to save, and then go ahead and calculate that stream or that corrosion rate value. Okay. So once it's done, As usual, we go to the general corrosion rate. And what do we see here? We see a very weird plot. It's hard to understand. I didn't change the units. I haven't been changing the units for the corrosion rates. We could have used mils per year. We could have changed the other units, but we haven't. So, but it's fine. Now, because this is a logarithmic scale, right? All the values are going to be here to the left, like towards the left. So what we need to do when we see this type of situation in the software is, oh, this is obviously a logarithmic scale, so we need to just change it to a logarithmic scale. How do you do that? You just right-click on the axis of interest and select the option logarithmic scale. Oh, now it's much better. I want you to focus your attention on the corrosion rate value. It's very small, very low. Basically, the seawater analysis is, the seawater sample is not doing anything to this stainless steel. But that's not true. We saw that boat that I showed you, that picture, there was corrosion, there was damage. It cannot be that I'm having such low corrosion damage. Virtually, this is saying that we are not corroding very, very high, or we are not damaging our material from a general corrosion point of view. So if we base our results only on general corrosion, we will be drawing the wrong conclusion, right? But when we go to the localized corrosion side, again, we need to change this here to a logarithmic scale. We see that, okay, at low concentrations of oxygen, okay, we see that the repassivation potential is above the corrosion potential, so you don't have localized corrosion damage. But as soon as you hit a specific value of oxygen, this is around 0.16 milligrams per liter of oxygen in solution, then you start seeing that the corrosion potential is above the repassivation potential, and you start seeing localized corrosion damage. The software also is producing or calculating the maximum pit current density of that pit that you're forming on the metallic surface. So one rule of thumb, when you see this maximum pit current density in amperes per square meter, that's the unit you need to use, is that 1 ampere per square meter is equivalent to 1 millimeter penetration depth for a pit. So these pits, according to the rule of thumb, are, if you are at 0.16 milligrams per liter, your pit could be as small as 0.2 millimeters. But as you increase the concentration of oxygen in solution, it can go up to 0.5 millimeters penetration on your surface. So you are, in fact, having localized corrosion damage, which is huge. It's going to have detrimental effects on your metallic surface. So again, you always couple this general corrosion rate behavior or corrosion rates values with the localized corrosion results to get a better or a bigger picture of what's happening with the material from a corrosion point of view. Okay, so main takeaway, you do have a concentration of oxygen that is critical for localized corrosion damage. Finally, here in the polarization curve, we can also analyze what happens. So let me just clear these reactions for a moment. So we start with virtually no oxygen, 1 times 10 to the minus 5 milligrams per liter of oxygen. And I'm going to add the anodic reaction with the oxygen reaction, and maybe, I don't know, maybe we have the bicarb. No, we don't have the bicarb. Maybe the reduction of hydrogen. Okay. So again, and maybe the corrosion potential. The corrosion potential is here, meaning that probably here is the water. Yeah, so I'm going to reduce. So in the first case, what was driving the corrosion, when you don't have oxygen virtually, what drives the corrosion is the reduction of water on the sample. You add oxygen above 0.16 milligrams per liter. So let's say you have oxygen 2.52 milligrams per liter. Now you see that this oxygen reduction reaction, right? Because it appears in the system, because you are adding oxygen to the system, now is driving or increasing that corrosion potential. You see it went from a value of around, I don't know what value is this, minus 0.5 to a value of 0.2. So it went from a negative value to a positive value. And that's the reason why you are seeing this increase here in the corrosion potential. And you'll see that repassivation potential does not have the oxygen concentration, doesn't have any effect on that repassivation potential. It virtually stays constant, but it is having an impact on the corrosion potential. And that's the reason why you start seeing localized corrosion damage after certain concentration of oxygen. Okay. So then the question is, which material do I use? If this 304 stainless steel is going to pit, so then what should I use? So you can always copy and paste this example here, go back to the molecular seawater, and change the metallurgy. Okay, so we can say, what if we don't use 304 stainless steel? What if we just go a little bit higher to 316, right? And we look for 316 in here. Let me know if I'm going too fast or not. Let's save. And since I copy and pasted the same calculation, so then I can go ahead and recalculate, right? And I can always go back to my original general corrosion rate. I have to put it in the logarithmic scale. Again, low, very low corrosion rate values. I do see now that at 0.2, more or less at the same composition or concentration of oxygen, is still susceptible to localized corrosion. So I don't think it's a good idea, right? It's not a good idea to use 316. So maybe we can go to a little bit higher or a better alloy. And this was an actual study we did for a company, and they came back, or they ended up using the 254 SMO alloy. So that's the one that we are going to use. It's going to be, I'm going to do the same here, right click, copy, going to paste, and I'm going to use a different metallurgy. I'm going to use 254 SMO. That's the one I'm going to use. Make sure that you change your metallurgy here. Look for alloy 254 SMO. So this, let me see one thing. So the 304 stainless steel, you can always analyze also the composition, right? So the 304 stainless steel had iron, or is mostly iron, 71%, chromium 19%, and nickel 9%, right? This is the composition. I just want to see if what is different in these alloys. So for example, the 254 SMO has less iron. Now instead of 71, it has 55.68. It has more chromium. It has 20% chromium compared to 19. It has nickel, more nickel, which is 18%. And it also has molybdenum. So this new metallurgy has molybdenum. And molybdenum is known to add inhibition or passivating properties to the alloy. Because as soon as a pit is happening or as soon as the passive film is damaged, the molybdenum kind of helps repassivate the surface again. So maybe this molybdenum is what is having a huge impact on, or we don't know, we will see. But this molybdenum could have a good impact on the corrosion resistance of this alloy. So we change it to this alloy, and then we click on calculate. And then we go to the general corrosion rate, logarithmic scale. The corrosion rates are even, the general corrosion rates are even lower, right? These are 1.6 10 to the minus 4 compared to, well, this is 3.8 10 to the minus 4, but it's lower. And virtually the same. Notice that it's like the same value no matter what oxygen concentration you have. It's the same value. What I want or I am interested to know is the localized corrosion piece. And you will see here, okay, at some point, virtually when it's basically the oxygen is saturated here, is where you start seeing that the corrosion potential is higher than the repassivation potential. But overall, like in most of the concentrations that we have studied, this alloy is not as susceptible to localized corrosion as the two first alloys that we studied. Okay. So I would recommend using this alloy for seawater applications to not, it will not, and you will see here to the right, is susceptible to localized corrosion a little bit, right? The penetration depth would not be that much, 0.01 millimeters in this case. And that's it. Let me see, what else do I have for this example? Any questions about this example? What we did and how we use the seawater analysis to recreate a sample and that then you can use for further understanding what is the impact of dissolved oxygen. This is a summary of what I was talking about before, if in case you forget what is the criterion that the software uses to tell you if we will have localized corrosion or not. This is the criterion. And in here in these plots, what I'm trying to, or what we're trying to show is that the repassivation potential will be affected by certain species or temperature, for example. If we have aggressive ions like chlorides, for example, it does have an impact on the repassivation potential, but not very much on the corrosion potential. If it's temperature also has an impact on the repassivation potential and a little bit on the corrosion potential. Oxidant, this is the example that we did today with oxygen. So the repassivation potential does not change very much or virtually nothing with oxygen concentration, but the corrosion potential does change. So whenever you have a crossover of corrosion potential and repassivation potential is where you will see localized corrosion. And another important piece that I would like to talk about is that the wider the difference between that corrosion potential that we predict and the repassivation potential that we predict, the greater the propensity for localized corrosion. So in this example here that I showed, in here we don't have bigger, like a huge difference, right, in the between the corrosion and repassivation potential. So we are predicting that you will have localized corrosion, but it's not the difference is not as wide. If the difference was wider, the propensity is much higher for that localized corrosion damage to occur. And finally, before I let you all go, I would like to talk about or mention that you can also, just like we did with the, yes, Pradeep, you have a question?
Yeah, Dan, I have a quick question here.
Sure.
When you plot the peak current density in the polarization curve and the net current density, so why the peak current density is less than the net current density? I was just wondering about it.
Oh, sure. That's a good question. Okay, let me just, this is 10 to the minus 5. Let's do this one. Let me just add less stuff to our conversation here. Which alloy is this? 254? 254, okay. So your question was why the peak current density doesn't match the net current density?
Yeah, I was just thinking like it matches at some point and then it diverts, right, at the end region, I guess.
It diverges. So the peak current density is calculated in a different way. There is a different algorithm for the peak current density. But how can I say this? Let me see. Let me think. Did we have localized for 10? I just need the better example. This one. Let's start with this one. So this net current density, as you remember, is the contribution of all the cathodic reactions, right? So if I add my oxidation of this chromium oxide, the reduction of water, this is the addition of all of these. The net current density is the addition of all of these half reactions that are happening. Okay, so they start being added, and that's what you get, the net current density. Now, the peak current density is another algorithm that was created for the repassivation potential. And there is a criterion that says that the repassivation potential should be, or any pit that reaches a 10 to the minus 4, no, a 10 to the minus, I think it's 10 to the minus 2, I don't recall exactly. But 10 to the minus 2 ampere square meter, that would be the repassivation potential. So this peak current density doesn't have to do anything with any contributions of cathodic or anodic reactions. It's just another equation that we use for the peak current density. And the repassivation potential criterion says that as long as it reaches a 10 to the minus 2 amperes per square meter, that would be the repassivation potential. So when you create the peak current density polarization curve and you put it on top of the net current density polarization curve, you will see if we had here an indicator like a little square here, you will see that the repassivation potential is higher than the corrosion potential. So visually here, in here we can see, we could say we are now having localized corrosion damage at this concentration, 0.01 milligrams per liter. But if we have localized corrosion damage, so then we would need to see the opposite. We would need to see that the repassivation potential value, the 10 to the minus 2, that crosses this red curve here, needs to be lower than the corrosion potential. So if we go to the 10, which is where we have localized corrosion, that's what we would see. And you'll see this is the peak current density again. It's used it's using another algorithm. It doesn't have to do anything with the cathodic and anodic reactions. And if you go to 10 to the minus 2 amperes per square meter, and you put it below the corrosion potential, you'll see that the repassivation potential is lower. It's right here, would be right here, than the corrosion potential, and that's why you're having localized corrosion damage.
I see. Okay. Thanks, Dana.
I do have to put, I'm going to write it down. There is a paper and there is the equation for the peak current density. And I should put it in my slides. This is a good question, and it would be nice to show what is the equation that we use for this peak current density value and the criterion. Okay. With this, I guess we can stop here. I was going to do another example where I was just going to vary both the oxygen and temperature and see the susceptibility, how temperature also plays an important role in seawater applications or produced water applications, and how susceptible a material can become when the temperature also plays, when the temperature is included as another variable. Okay, so with this, I think I'm going to stop here. Are there any other questions? Mariana, Joaquin, anything that you would like to have seen? Maybe I can send examples, chapters, anything, questions that you may have, etc.
Thank you, Dana. No, nothing specific about this. Probably I will send you a paper related with the quantity of oxygen, and the different steels that were evaluated, just for you to have it, as we discussed it previously. No, we will continue asking you some things.
Sure, yeah.
Specific and related. So thank you for your time, and thank you for all your explanation.
Oh, sure. This is the links for the resources I used for this training. So if you have any further questions, or if you want to know more about a specific example, you can always come to these chapters and read a little bit more about the peak current density and things like that. Oh, here, I did write it, Pradeep, here, peak current density. You have access to that. All of these links, you can just simply click and it will take you to the respective manuals. And this is where you're already familiar with the portal. So this is where you can submit your questions. And this is my information if you have any questions when you want to reach out. But thank you so much all for your time. I'm looking forward to hearing from you. What else do you have usually, like grow our application range of what the corrosion analyzer can do in the industry. And thank you guys from the software team. There were not very many bugs this time. Usually when the software people are not here, I see bugs, or not bugs, but like little things in the software, But this time it worked perfectly. Except with the units that Joaquin had. Joaquin, if you could send me that file, I could take a look to see why the units were changing from batch to flowing. Something that I couldn't figure out. Okay. Okay. So with this, I will let you go. Have a wonderful rest of your day, and it was nice working with you.